Okay, welcome back to this video in AP Calculus. So without further ado, let's get started on the first problem. So we're looking at this graph of f prime of x, and we're first asked to identify all intervals where f of x and f prime of x are increasing, decreasing, and constant. So first let's look at f prime of x, because that's a bit easier. It's going to be increasing when the function is going up. So it looks like it's increasing from -1 to 0, and from 1.1 to 2, right? -1 to 0 is this part, 1.1 to 2 is this part. That's when it's going up. So in this interval, it's increasing. And then from 0 to 1.1, it's decreasing, right? F prime of x is going down. So now let's look at f of x. F of x, now you need to know the relationship between the graphs of f prime of x and the graphs of f of x. So when you're looking at the graph of f prime of x, when that graph is negative, your function is decreasing. And when that graph is positive, your function is increasing. So from -1 to 1.7, that's all of this section here, your function is negative, your derivative is negative, so the function is decreasing. And then from 1.7 to 2, your derivative is positive, so your function is increasing. It has a positive slope. Okay, so that's part A. Now let's look at part B. Part B asks to identify and classify all critical points for f prime of x. So the critical points is when you have something interesting going on, right? Your slope is 0, you have an undefined slope, you have a cusp, something like that. And we notice that at this point here and at this point here, we have a slope of 0. So those are two critical points. So the critical points are 0, 0, and I'd say that looks to me like 1.1, -1. And we're asked to classify these as well. So for 0, 0, this is like the top of a hill. So it's like a relative maximum. It's a maximum of that part. And then this second area here is the bottom. So it's the relative minimum. Okay. And then for part C, we are asked to find where the absolute minimums and maximums of the graph occur. So one quick thing I want to point out that's really important is when it asks where the minimums occur, that means we're talking about x values. The word where means they're asking for x values. If they instead asked find what the absolute minimum and maximums are, if they asked you instead what they are, then you'd give the y values. Okay, so what they are, y values, where they are, x values. So here we're asked where they are, so we're going to say the absolute maximum is where from -1 to 2 the graph has the highest value. And that looks like this point right here, that's where the function is the highest. So absolute maximum is at x equals 2. Again, we're given the x value. And the absolute minimum is when the graph is the lowest. So that's down here at x equals -1. Okay, so now before we do part D, I'm just gonna kind of erase this stuff just to make room, because I don't want to keep scrolling up and down to look at the graph. Okay, so for part D, and I kept part A up for a reason. We're asked to sketch a graph of f of x and confirm your answer with your predictions from part A. That's why I left this up. Okay, so we're asked to sketch f of x, right? We're going to sketch f of x. And let's see. So when you're looking at the graph of the derivative, we can say that, okay, so when there's an x-intercept, right, x-intercept on the derivative, that corresponds to a max or min on our original function, on f of x. Okay, so at x equals 0 and x equals 1.7, we're going to have a slope of 0. Okay, and another thing is that when we have the graph is negative here, the graph is negative from -1 to positive 1.7, that means our function is going to be decreasing. So a negative f prime of x means that f of x is decreasing, and then it's going to be the opposite for a positive graph. A positive f prime of x means the function is going to be increasing. So with that out of the way, let's start actually drawing our function. So I'm just going to start around here, and then so up until the value of 1.7, we're going to be decreasing the entire way. Okay, but at 0, there's going to be a break where there's going to be a slope of 0. So we're going to decrease, and then we're going to have a slope of 0 here, right? So this is our point where we have a slope of 0, and then from 0 until 1.7, we're going to continue to decrease. We're going to continue to decrease, and then at 1.7, we're going to have another slope of 0. That's a terribly drawn graph. But we're going to have a slope of 0, and this is at 1.7, right? And then after 1.7, you see we're going up. So we're going to have a positive graph. It's going to be increasing. Soon it's going to be positive, it seems like. So this was a graph of the derivative, the opposite of the derivative. You'll learn later it's an integral. So if we take the derivative of this graph, we're going to get this graph. And let's think about this. It looks like this is a 4th degree function, and that makes sense because if you take the derivative of a 4th degree function, you're going to get a 3rd degree or a cubic function. So, and let's check our answer with part A. From -1 to 1.7, the function is decreasing, so it's going down, and then from 1.7 to 2, the function is increasing. So we checked our answer from part A, and it's consistent with that. Okay, so now let's look at part E. For part E, we are asked to find all points that satisfy the mean value theorem. So I'm assuming they're talking about for f prime of x, because that's what we're given. So I'm just going to quickly redraw f prime of x here, like a rough sketch. And then, so now I'm going to draw the average rate of change. I'm just doing my best estimate here. So the average rate of change looks to be something like that. It's from the final point to the initial point. I'm just drawing a straight line. That's the rate of change. And remember, the mean value theorem says that there are some points, if this function is continuous and differentiable, which it is, there's going to be some points where this average slope is going to be equal to the derivative. So this slope looks to be the tangent line at maybe around here, and maybe around here, I want to say like right here. And then now they want the actual points, so we can estimate here. It doesn't have to be exact. I'm going to estimate this is -0.5, comma -0.2, and 1.4, comma -0.8. Again, these are just estimates, and these are approximately the two values that satisfy the mean value theorem for this function. Okay, so that was question 1. Okay, so for question 2, we're given an equation this time instead of a graph. And so on the interval -1 to 2, we're asked to find these 4 things. So first, for part A, let's find the relative extrema by first and second derivative tests. So the first part of the process for both of the tests is going to be the same. We're going to take the derivative and find our critical points. So let's take our derivative, f prime of x, and using the power rule, we're going to get 4.5 x squared minus 5x. And we're going to set this equal to 0. 4.5 x squared minus 5x equals 0. And we're going to use our algebra skills. X times 4.5x minus 5 equals 0. So x is going to be equal to 0 and 10/9. And both of these numbers are in our interval -1 to 2, so we're good to go on to the next step. So the next step is going to be, we're going to use our test. So first and second. So in our first derivative test, we're going to draw our number line. We're going to plug in 0 and 10/9, and we're going to plug in numbers in each of these sections. So we're going to plug in a number that's less than 0, a number that's between 0 and 10/9, and a number that's greater than 10/9. And we're going to plug that into our derivative. So what I like to do personally is I like to plug in a really crazy large or crazy small number on the ends here, because it just makes it really clear in my mind if it's going to be negative or positive. Like for example over here for the negative section, I'm going to plug in negative 10,000, and I'm going to get a really crazy positive number minus a much smaller positive number. Or actually it's going to be a minus a negative number, so this is definitely going to be positive. And then on the positive side, I'm going to plug in 1,000,000, and I'm going to get a really big positive number minus a little bit of a smaller positive number, and I know this is going to be positive. And then in the middle, I'm going to plug in 1. I'm going to get 4.5 minus 5, which is negative. And then so I see from here to here, it's positive to negative. So I know that 0 is a relative maximum. And then here I'm going from negative to positive. So 10/9 is a relative minimum. And then they're asking for the relative extrema. So I'm going to give the y values. And that's just going to be done by finding f of 0 and f of 10/9. So f of 0 is just going to be 0, and then f of 10/9 is going to be negative 1.0288. Okay, and now let's see what we can get if we use the second derivative test. So for the second derivative test, we're going to take f double prime of x, and we're going to get 9x minus 5. We're going to plug in our two critical numbers that we found. So we're going to find the second derivative of 0, and then the second derivative of 10/9. Okay? If you plug this in, you're going to get negative 5, and then positive 5. Since this is a negative number, we know that this is a relative max, and since this is a positive number, this is a relative min. So by our second derivative test, we've concluded that 0 is a relative max and 10/9 is a relative min, and then we'd plug that in back into our original equation to get the y values again. I'm not going to do that twice. Okay, and then I'm just going to erase this just to save space. Okay, so in part B, we are asked the x values of all absolute extrema. So to find the x values of all absolute extrema, we're gonna find the y values for the endpoints, so -1 and 2, and then we're also going to find the y values for our critical numbers. If you remember from part A, the critical numbers were 0 and 10/9. I'm going to find f of 0 and f of 10/9. I've already done this in advance to save time. This is -4, this is 2, this is 0, and this is -1. Okay, and then the smallest of these is going to be so this is our smallest. This is our relative minimum, or sorry, not our relative minimum. This is our absolute minimum, and this is our absolute maximum because it's our greatest. So, and we're gonna, it's asking us for x values here really explicitly. So our absolute minimum is at x equals -1, and our absolute maximum is at x equals 2. Okay, that's part B. So, alright, part C. Intervals where f of x is concave up and concave down. Okay, so that we're going to look at our second derivative. To find concavity, we need to look at our second derivative, which is 9x minus 5. And then we're going to do the number line thing that we do for the first derivative test. We're going to do that with our second derivative. So the critical point here is x equals 5/9. And if we plug in a number greater than that, we're going to get a positive number. If we plug in a number smaller, we're going to get a negative number. And then so we want to find out where it's concave up and concave down. So if it's positive, here's where it is concave up, and here's where it's concave down. And then also remember, we have endpoints here. It's from -1 to 2. So when I write my final answer, it's going to be concave down on -1 to 5/9 and concave up on 5/9 to 2, because those are my -1 and 2 are my endpoints. So that's my final answer for the concavity part. And then for part D, where we're asked for the inflection points, that's just going to be where the concavity switches. So in this case, we're concave down over here, we're concave up over here. This is the point where it switches concavity 5/9. So the concavity is going to switch at x equals 5/9. This is our inflection point. And if you wanted to, you could find f of 5/9 and get like a coordinate. So that's our answer for part D, and we are done with question 2. Okay, so for the next problem, this is a optimization problem. So we have a rectangular field, we're given the sides, the cost of each of the 4 sides, and we're given the amount of money we have. And so we need to determine the dimensions of the field that will enclose the maximum area. So the first step here is we're going to draw a picture. So we have a rectangular field. The top is $7 per foot. The bottom is $2 per foot. And the 2 sides are each $10 per foot. And then if I call this side X and this side Y, the total cost of my fencing is going to be 7 times X plus 10 times Y plus 2 times X plus 10 times Y, because I'm multiplying the number of feet times the price of the fencing per foot for each of the 4 segments. And remember, my total cost is going to be 700 because that's how much money I have. And if I simplify this a bit, I'm going to get 9x plus 20y equals 700. And then the function I'm trying to maximize is the area, and the area is going to be x times y. Okay, so I can take this top equation and I can solve it for y. So you can also solve it for x, it's just a matter of which one you prefer. So I'll get 20y is equal to 700 minus 9x, and then y is equal to 35 minus 9 over 20x. And then I can plug this back into the equation that I'm trying to maximize. So this can be x times 35 minus 9 over 20x. And then I can expand this out. I'm going to get 35x minus 9 over 20x squared. And I'm going to call this my area function, a of x. Because remember, this is x times y. This is the area of the shape. So I want to maximize this. So the way we're going to maximize it is we're going to take the derivative and find our critical points. So let's take a prime of x. A prime of x is 35 minus 9 over 10x. And then we're going to set this equal to 0. Make sure you do this on a separate line. So this is one line and this is another line. And then I can add 35, multiply, and divide by 9. And I'm going to get x is equal to 350 over 9. And then let's use our second derivative test to figure out whether this is a maximum or a minimum. So a double prime of x is going to be negative 9 over 10. This is always negative. So that means this is going to be our relative maximum, since our second derivative is negative. Okay, so now what we're going to do is we're going to say, alright, so if this is my x value for the maximum area, what's my y value? Well, remember up here, we have the equation y equals 35 minus 9 over 20x. So I can say y equals 35 minus 9 over 20 times my x value. And this comes out to be 35 over 2. So this is my maximum x. This is my maximum x dimension. This is my y dimension. So these two this combination of this x and this y, that's going to give me the maximum area. So I'm going to rewrite this. 350 over 9 feet by 35 over 2 feet gives the maximum area. Because this is the 2 points that will give us the relative maximum. And with that, we are done with this optimization question. Let's move on to the next one.
Okay, for the last problem, we have a rectilinear motion problem, or a particle motion problem. So we're given the equation for the particle's position as a function of time, and we're going to find all these things. So let's start with part A. What is the velocity at time t? So the velocity function v of t, that's just going to be the derivative of the position function. So we're going to take the derivative of f of t using the power rule, and we're going to get 3t squared minus 18t plus 15. Okay, and that's our entire answer for part A. And then for part B, we want the velocity after 2 seconds. We're just going to plug in 2. V of 2 is 3 times 4 minus 18 times 2 plus 15, which is 12 minus 36 plus 15 is negative 9 feet per second. And the feet per second is coming from the units for position divided by the units for time. For part C, when is the particle at rest? That's when the velocity function is 0. So I'm going to write my v of t. And I'm going to set this equal to 0. I'm going to divide both sides by 3 to make it easier to factor. And then I'm going to factor this, and I'm going to get t minus 5, t minus 1. So my t is equal to 1 and 5. And it's great that these are both positive numbers. If one of them were negative, then we would have a problem because you can't have negative time, and that answer would not count. So since we have both positive answers, these are both valid times where the particle is at rest. For part D, when is the particle moving in the positive direction? That means we're going to have to draw our number line for the velocity function. We're going to plug in our two critical values of 1 and 5, and let's check our signs. If we plug in a really big negative number into this, we're going to get a negative number times a negative number, which is going to give us a positive number. If we plug in a really big number, like 10,000, we're going to get a positive times a positive, which is positive. And if we're plugging in, let's say 2, we're going to get a negative times a positive, which is going to be a negative. So we want to find out when is the particle moving in the positive direction. That's going to be when it's a plus sign. So it's going to be positive from 0 to 1, and from 5 to, well, it's going to go on positive forever, so 5 to infinity. And we always put parentheses here. That's just a matter of, that's just how it is. So this is when it's moving in the positive direction. Okay, so now for part E, I'm going to erase these things here just to make some space. So how much greater is the total distance in the first 8 seconds compared to the total displacement? So to find the distance, I'm going to find out the individual distances of each leg of its journey. And by each leg of its journey, I mean each different section that we made here. We took the velocity function and we split it up into 3 different functions based on its signs. So we're going to find the sum of each of these sections, and that's going to be the total distance. So we're looking at the first 8 seconds, right? So we're going to have the distance at 1 minus the distance at 0, the position at 1 minus the position at 0, plus the position at 5 minus the position at 1. So that's this middle segment here. And then the position at 8 minus the position at 5. Right? 8 is because we're only looking at the first 8 seconds. And then since I want this to be positive, since distance is always positive, I'm going to take the absolute value of all these expressions. And I already did this just to make life easier. We have 7, 32, 81. It's going to give us 120 feet. But we are not done yet. We want to find out how much greater the distance is compared to the displacement. So we need to find the displacement. That's a lot easier. That's just going to be our final position minus our initial position, and our final position is 8 because we're leading with the first 8 seconds. So the position at 8 is 66, the position at 0 is 10, so the distance, the difference between those two is 56 feet. And we want to find out how much greater is 120 than 56. That's 120 minus 56 is 64 feet. So this is our final answer. It is the difference between the distance and the displacement. Now notice whenever you're dealing with this kind of problem, your distance is always going to be greater than your displacement. If you have a greater displacement, you did something wrong and you're going to want to check your work. Okay, so now let's move on to part F. So part F asks, when is the particle speeding up, when is the particle slowing down, and justify. So for part F, let's look at speeding up and slowing down. So we need to look at both the velocity function and the acceleration function. So we need to draw our diagrams for both. I'm going to redraw the diagram for velocity up here. So we have a plus, a minus, and a plus. And then for acceleration, from acceleration function, the acceleration is the derivative of the velocity. So it's going to be the derivative of, so remember my velocity was 3t squared minus 18t plus 15. So my acceleration is going to be the derivative of that. It's going to be 6t minus 18. And then I need to find my critical points to put in my number line. So that's going to be t equals 3. I'm going to plug that on here, t equals 3. And then if I plug in a number greater than t, it's going to be plus. And if I plug in a smaller number, it's going to be minus. So now we can move on. We're going to look at the signs. So when the two functions, velocity and acceleration, when they have the same sign, so when v of t and a of t have the same sign, it's speeding up. If they have opposite signs, you can probably guess what's going to happen. They're slowing down. Okay, so I'm going to look at my signs here. From 0 to 1, it's slowing down because they have opposite signs. Right, from 0 to 1, it's slowing down. And from 3 to 5, it's also slowing down because you have a negative and a positive. So from 0 to 1 and from 3 to 5, it's slowing down. And it wants to justify. So we're going to say this is because f prime of t and f double prime of t, these are my velocity and my acceleration functions, have opposite signs. Okay, and then when I look at this from 1 to 3 and from 5 to 8, there's the same sign, a positive and or negative and a negative, and a positive and a positive. So from 1 to 3 and from 5 to 8, they're speeding up because f prime of t and f double prime of t have the same sign. So this is the answer for part F. And with that, we are done with the review for this unit in AP Calculus. I'll hope to see you in the next video. Goodbye for now.